Welcome, fellow physics fans. I'm Dr. David Corral, an assistant professor of physics at Centenary College of Louisiana. I would like to thank the Attaway Professorships in Civic Culture program at Centenary for underwriting this event. We're very excited today to have Dr. Paul Halpern as our guest speaker this evening. Dr. Halpern is a professor of physics at the University of Sciences in Philadelphia. He's the author of 17 books and numerous articles on space, time, higher dimensions, and the cultural aspects of science. These books include the widely read classics of popular physics, Einstein's Dice and Schrodinger's Cat, and The Quantum Labyrinth. Halpern has received a Guggenheim Fellowship and a Fulbright Scholarship, and he has appeared on C-SPAN, the History Channel, the Discovery Channel, and the PBS series Future Quest, as well as The Simpsons 20th Anniversary Special. Tonight, Dr. Halpern will be discussing his new book, Flashes of Creation, George Gamow, Fred Hoyle, and the Great Big Bang Debate. It's a great book. It tells the fascinating story of two scientists who made permanent contributions to the debate around the origins of the universe. Dr. Halpern has agreed to answer questions after his talk tonight. So if you are joining us remotely, please feel free to share your questions in the chat, and I will make sure they're answered at that time. Those of us who are in person tonight can come forward and take a gander at the microphone. Please join me in welcoming Dr. Paul Halpern.
Thank you. Thanks to Centenary College and especially to Dr. David Corral for inviting me. I'm really delighted to be here. I wish I could be with all of you in person, but logistically it didn't work out. So I'm happy to be here by Zoom. So I'm going to share my screen now and with a PowerPoint and talk a little bit about my book and about the lives of two great scientists and how they interacted. Okay, so hopefully everyone can see my screen now. And so this talk is about my book, Flashes of Creation. And I'm going to talk a little bit about George Gamow, Fred Hoyle, and the Great Big Bang Debate. Now, a lot of you, or most of you probably have never heard of George Gamow or Fred Hoyle. When I was growing up, they were two big figures, not just in science, but in science popularization. So I remember picking up one of the books by George Gamow called 1, 2, 3, Infinity, and that helped inspire me to become a scientist. So I still recommend the books by these two figures. So let's take a step back in time. Looking back over the millennia, there are several questions that many people have tried to answer. One question is, did time ever have a beginning, or did everything last forever? Another question is, if time did have a beginning, what happened at that genesis? How did the universe come into being? What specific material came about when the universe emerged? In what order? How large is the universe? What's its extent? The extent of the universe has changed over the centuries. People have grappled with the idea that the universe is much, much bigger than once thought. And finally, the ultimate question, will the universe someday perish, or will it last forever in some form? So until the 20th century, and we're talking about really until about 100 to 110 years ago, there was really no accurate way of answering these questions through science. There was no experiment you could really do with the universe to try to figure out how old it was, what it was made of. So what happened was philosophers debated. So you had philosophers and religious thinkers who were debating the extent of the universe, the origin of the universe, what is it made of, and came up with many different theories. However, in the early 20th century, there were several key revolutions that changed the course of science. One such revolution was the relativity revolution, special and general relativity. Another revolution was the quantum revolution. Now, two figures who you're probably more familiar with were involved in those revolutions. Albert Einstein, who took a role in the early development of quantum physics and also was the developer of special relativity and general relativity, and Niels Bohr, who was one of the founders of quantum physics and then eventually nuclear physics. So I'm not going so much into special relativity, which is Einstein's theory of what happens at very, very high speeds, speeds close to the speed of light. But general relativity, the successor theory, plays a role in this story. General relativity is Einstein's theory of gravity. And Einstein's theory of gravity is that gravity is the warping of space-time, as if space and time itself is kind of a blanket, and that blanket has wrinkles and curves and creases, and these all represent the effect of mass on the universe, and those in turn lead to changes in motion. And that was developed in 1915. This is one of Einstein's key papers. In German, it says the field equations of gravitation. And then in the same year, a physicist we're going to be talking about a lot in this talk was born. Fred Hoyle was born in a house in northern England in a very working class village, which I had the opportunity to visit during my research, called Bingley, in the relatively remote area of Yorkshire. So this was not a posh part of England, but rather a working class, middle class part of England. Now, back to general relativity, one way of summing it up, said by the brilliant physicist John Wheeler, is space tells matter how to move. Matter tells space how to curve, meaning that if you have space that is indented, curved, then objects such as planets want to move not in straight lines. They try to move in straight lines, but they end up moving in orbits, elliptical orbits. And what causes that curvature? More matter, such as the sun. So the sun, by being in this region of space-time, places a dent, a giant dent, and that creates a gravitational well, and then the planets have to move. When they try to move in straight lines, they move in what are called geodesics, which means curved paths, and they move in elliptical orbits. And that's how Einstein explains gravitation. Unlike Newton, who said that gravitation is action at a distance, which Newton imagined kind of an imaginary string pulling the planets, Einstein came up with a more sophisticated argument involving warp space-time. Now, needless to say, Einstein was born in the 19th century, and he had certain prejudices. Everybody has scientific prejudices. And Einstein thought that even if local parts of the universe, like near Earth, could be bumpy, curved, and so forth, and dynamic, he wanted the overall universe to be stable. He wanted it to be static, because that was what Newtonian theory predicted. That's what astronomers thought. They thought that the stars moved in the sky, but that the sky itself was a stable framework. So Einstein tried to come up with solutions to his equations that were stable, but the only solutions he could find were either expanding or contracting. None of them were stable. So he decided reluctantly to add a kind of fudge factor to the equations called the cosmological constant term. And what it did is it allowed for stable universes. And it was very, it wasn't very elegant, wasn't very beautiful, unlike the original theory. It was like looking at the Tower of Pisa, which is a beautiful edifice, that happens to be leaning, and then adding steel girders to scaffold it to make it stable. It's not very elegant. So let's move on to another thinker, Russian physicist Alexander Friedmann, who worked at a time when Einstein's general relativity had already come out. Friedmann's occupation was a meteorologist. He liked to launch weather balloons and take measurements of weather readings. But like many scientists at the time, they had hobbies and other interests. And he looked at Einstein's equations, and he looked at the form without the cosmological constant and came up with expanding and contracting solutions. So he came up with solutions that would expand for a while and then they would collapse, or some that would expand forever. And today we call those a big whimper solution or a big crunch solution. Big crunch is where the universe starts recontracting. So we can think of this ironically because Friedmann was an expert in weather balloons. You can think of this as a bit like a balloon. Imagine objects in the universe, which we now know to be galaxies, painted on the side of a balloon, and then you blow up the balloon. Well, these galaxies are going to get further apart as the balloon expands, and they're going to be equally further apart. So there's no real center of expansion. Everything is expanding equally. So that's what later would become called the Big Bang. Now, a student in Friedmann's class was the young thinker George Gamow, who was from Odessa in the Russian Empire. And he was studying in a city that has had many different names. It originally was called St. Petersburg, then became called Petrograd, then became Leningrad under the time of the Soviet Union, which is when George Gamow was there. And now it's back to being called St. Petersburg again. Gamow took a course in general relativity with Friedmann and became fascinated by it and wanted to work with Friedmann. But alas, Friedmann went up in a weather balloon in 1925. He caught cold, and then I don't know if this was related, but sometime later he went on a vacation, caught typhoid, and his health deteriorated and he died at a very young age. So Gamow was left without an advisor. But nevertheless, Gamow continues interest in the cosmology. Now let's look at the United States. In the United States, astronomer Edwin Hubble was making observations of the objects in the universe which he found were galaxies, independent island universes in their own right. Until the time of Hubble, we thought that these were gas clouds in the sky. So Hubble showed that these gas clouds were galaxies in their own right, just like the Milky Way. And he also proved that these were expanding away from our galaxy, for the most part, faster and faster as they moved further away. Hubble never concluded that this meant that the universe was expanding, but practically everybody else did. They took Hubble's data and said, wow, the universe is getting bigger over time. Now, little known fact, Hubble was also a fantastic basketball player. He played for the University of Chicago in 2 winning seasons and then became a basketball coach in Indiana. But luckily, he turned to astronomy and made his mark in astronomy. Here's Hubble's data, and you see that as you go further out in the universe, if you plot the galaxies, they are faster and faster. This is speed, this is distance. And some of you who are physics majors might have to do this for labs. You take a scatter plot, and then you draw the best fit straight line. And this best fit straight line is now known as Hubble's law, which says that the farther out galaxy is, the faster it's moving, which is a sign of an expansion of the universe. Now, around the same time, George Lemaitre, who was a cosmologist and priest, was developing his own theories of an expanding universe. And he had a theory actually before Hubble. And then when Hubble made his discovery, he quickly revised that theory into this idea of a primordial atom, a giant atom that encompassed all the matter in the universe, everything under the sun, everything under all the stars was all compressed to a single clump. And that clump expanded, and that's what created the universe. He was also a priest, but strongly believed in keeping science and religion separate. So here's a picture of him with Albert Einstein. So here's his book, The Primeval Atom, which was a hypothesis of the origin of the universe. By that time, Einstein was sold on the idea that the universe is expanding, and he later reportedly said to George Gamow that the cosmological constant was his biggest blunder. He should have put it in. Another question that was being talked about at the time, related not to the universe but to stars, was how do stars shine? And people started to think it had something to do with nuclear physics, and that stars shine by building up elements in their core, starting with the simple element hydrogen, and then building that up to helium, and then to higher elements. George Gamow, who's on the right here, right-hand side, talking to John Cockcroft, another physicist, played a big role in this idea. Because George Gamow studied the process called fusion. Fusion is where atoms merge together and create energy. Gamow showed how fusion could take place because of quantum probability rules. When two atoms get together, there's an energy barrier, kind of force field between them because they're both positive cores. Positive and positive don't like each other. They don't like to get together. But there's a process called quantum tunneling where the particles can break through a barrier with a certain chance and unite with each other, and the process of fusion begins there. Gamow sketched out that theory in one evening. He came up with the idea, took him one evening, and then the next day he showed it to other physicists. Here's my theory of quantum tunneling and fusion, which was really, really remarkable. And that theory was used to create the first particle colliders or atom smashers. So Gamow became a really big name in science. Now, he was in the Soviet Union, which became increasingly oppressive because the Soviet government tried to get the scientists to follow its ideology rather than scientific principles. So Gamow didn't feel he could continue to work there. At that time, he just got married to a woman named Ro. So he wanted to escape. He first did trying to escape with a kayak on the Black Sea. He wanted to go to Turkey, which was across the Black Sea from the Soviet Union, and defect. But after a couple of days, it was very stormy weather, and he was blown back to shore, so he couldn't defect that way. But remarkably, Niels Bohr managed to get him an invite to the 1933 Solvay Conference, which was a big scientific conference. And Gamow managed to twist some arms to get his wife an invite to the same conference under the pretext that she needed to help him with his physics. So they both went legally to the Solvay Conference in Brussels, and there they defected to the West and ultimately moved to the United States. Once in the United States, he got invited to George Washington University, which is in Washington, D.C., but he accidentally bought a ticket to Seattle, Washington, state of Washington, because he got mixed up. It's confusing because there are a lot of Washington universities in the United States, all over the United States, so he happened to choose the wrong ticket. But he eventually ended up at George Washington University. Now, meanwhile, Fred Hoyle would go to Cambridge University. Fred Hoyle studied astronomy and physics and then became a leading physicist with an interest in astronomy at Cambridge University. Now, Hoyle was also interested in the question of how stars make elements. He thought the hot cauldrons of stars was another place to make elements. He met with this remarkable astronomer named Walter Baade, who had a theory about supernova spewing out elements into space. And Hoyle said, that's it. The elements are made in the cores of dying stars, and all the elements could be built up in the very, very hot core of dying stars. And then when there's a supernova, which is a stellar explosion, these elements are strewn into space, and then they form the seeds of new star systems. So you may have heard the expression from Carl Sagan, we are made of star stuff, and that's in fact true. Everything on Earth, practically, including carbon and iron in our bodies and so forth, was made in a star that died billions of years ago and exploded, and the supernova took all the material and spread it out through our part of space, and that material eventually coalesced and formed the solar system. So it's amazing that the carbon, oxygen, all the higher elements in our bodies were once in the core of another star that lived billions of years ago. Now, hydrogen and helium are a different story, as we'll see in a few minutes. So here's Hoyle's idea that as a star dies, its core heats up and it starts burning all different kinds of materials. So it starts with hydrogen fusion, switches to helium fusion, and then helium burns at a very high temperature, switches to carbon, oxygen, and so forth. Finally reaches iron. Once that happens, the star experiences a crisis. And if it's a very, very massive star, the core implodes, the star explodes in the supernova, and in the supernova itself, that's where the remainder of the elements are produced. So for example, the highest natural element, uranium, was produced during an actual supernova at the point of explosion. Now, around the same time that Hoyle was developing this theory, he and some of his friends and colleagues, Thomas Gold and Herman Bondi, went to a horror movie. So this seems like a little bit of a switch of topics, going from astrophysics to a horror movie. Well, the horror movie was called The Dead of Night. And it was a strange movie because the beginning of the movie and the end of the movie were tied together in a kind of a plot twist. The movie involved somebody who goes to a house, experiences all these nightmarish circumstances, and has a strange feeling that he had dreamed about all these things. So during all these nightmarish circumstances at the house, he feels like he had done everything before and that things are going to end badly. And in fact, things do end badly. And I'm not going to give away too much of the plot, but it involves a dummy named Hugo, ventriloquist dummy, that comes to life and is a very, very evil character. At the end of the movie, all these terrific things happen. And then the main character wakes up and he realizes that it was all a nightmare. It really didn't happen. Or did it? He gets a call from the same house inviting him to go back to that same house. And he goes there and experiences all these horrific things again. And the idea is that this will happen again and again and again. So if you walk into that movie, doesn't matter what point you walk in, the whole process is going to play out the same way. So when Bondi, Gold, and Hoyle left the film, they went back to Bondi's apartment, had a few drinks, and Gold said, what if the universe is that way? What if things pretty much repeat themselves again and again rather than starting at a single point? So this was a theory to contrast with the Big Bang theory, to contrast with Lemaitre's theory and Friedmann's theory. And the theory is that the universe expands, but new galaxies fill in the gaps. Those new galaxies come from new stars. Those new stars come from the coalescing of new material. New material clumps together. And where does that material come from? It trickles in very slowly into the universe. So slowly we don't notice it. So slowly new material trickles in, it clumps into stars, they form galaxies, and these new galaxies fill in the gaps. So you see, unlike the balloon picture from earlier, the universe looks roughly the same over time, the same density, the same overall picture. So that means the universe can last forever. So meanwhile, around the same time, so we have all these stories going on. Gamow found a research student named Ralph Alpher, and they developed a completely different way of explaining how the elements in the universe formed. And that idea is now called Big Bang nucleosynthesis. Their idea was that all the elements were produced in the hot early universe during the early moments of the universe. And they published a paper which happened to be published on April Fool's Day. And to make the paper seem sillier, Gamow was a jokester and a prankster and a punster. He loved jokes. And his student was named Alpher. And he noticed that if you say Alpher Gamow, it's like saying the first and third Greek letters, alpha and gamma. And he happened to know a physicist named Hans Bethe, who was a big nuclear physicist. And he said, let's add beta to the name of the paper, to the authorship of the paper, to make a pun, alpha, beta, gamma. And Hans Bethe only found that later and enjoyed the joke and agreed to it. But Alpher was kind of upset because Alpher was the one who did most of the work on the paper, and he had to share credit not just with his advisor, but with Hans Bethe. Now, Alpher called the early substance in the universe, he didn't call it the primeval atom, he didn't call it the Big Bang, he called it something called Lem, which is a medieval Latin term for matter. So if you look in a medieval Latin dictionary, there's a term for matter, which is called lem, which stems from ancient Greek. And when they finished their paper, they celebrated by taking a bottle of liqueur and putting lem on the label and celebrating. Now, after they announced their discovery, or their paper, I should say, that all the elements were created in the early universe, they had estimated that that whole process would take only 5 minutes. And that led to a cartoon, and this is in 1948, only a few years after the first atom bombs exploded, of a bomb being kind of confused how the universe could have been created in 5 minutes. So that was a cartoon that appeared in the Washington Post. But there was a problem with their model. The early universe cools down very quickly, and it does not allow for any elements past helium. So you can produce helium from hydrogen, but you can't produce carbon from helium. So that was left to Hoyle's theory that you use hot stellar cores. So it turns out that the story of the universe involves a combination of two theories: a Big Bang that produced all the helium, and production in the cores of stars, which produced all the rest of the elements, such as carbon. So if you go to a birthday party, you can thank Hoyle for all the people being there, all the celebrations, and you can thank Gamow for the helium and the balloons. The term Big Bang Theory was actually due to Hoyle. He was on BBC Radio in 1949, and he was dissing the idea of the universe being created all at once. Not just Gamow's idea, but Lemaitre's idea, Friedmann's idea. He said, well, the steady state theory is much better because then matter is produced very, very slowly, trickles in. You don't have to explain why all this stuff appears at once out of nowhere and explodes. He thought that was ridiculous. So he called it the Big Bang Theory. That was way before the television show, and he was the one who came up with the name. So I don't know if the people of the television show had to pay the Hoyle family royalties. I kind of doubt it because it's a general term, but that's where the term comes from. Both of them were experts at popularizing their ideas. They weren't just great scientists. Uniquely, they were also great popularizers. So if you were to go to a bookstore in the 1950s, imagine this, and you had a little bit of money, you had some change, you could pick up George Gamow's book, The Creation of the Universe, which talked about the Big Bang Theory, for 50 cents, and The Nature of the Universe by Hoyle with the Steady State Theory for 35 cents. So I haven't bought textbooks for a while, but I hear that student textbooks are a little bit more expensive now than 35 cents or 50 cents, even in paperback. So that's what I hear. So they also wrote popular science books, science fiction. Gamow came up with the Mr. Tompkins series, which imagines a banker stumbling into all these weird quantum and relativity worlds. He came up with 1, 2, 3 infinity, which I mentioned at the beginning of the talk was inspiring to me. And then Hoyle came up with all these cool science fiction books and TV shows. The Black Cloud, which is about an intelligent cloud of energy. A for Andromeda, which is about aliens arriving on Earth. Gamow was also a funny cartoonist. He did the sketches. Here's one of his early ones where he imagined Niels Bohr as Mickey Mouse, and Mickey Mouse explains quantum physics. This was only 1 year after Mickey Mouse was created. George Gamow made this satire. So it's pretty remarkable. Or a few years after, I should say. And then here's one of two physicists, Ulam and Teller, competing to create the hydrogen bomb. Hoyle wrote operas. So he wrote the libretti for 2 different operas, including one about Copernicus, which is remarkable. And so there was this big rivalry, steady state versus Big Bang. So if you grew up in the 50s, you know, even kids in the schoolyard might have these debates. Did the universe last forever? Oh no, it began in a Big Bang. So you might take bets on which is true. And one of the problems with the early Big Bang theory is that in the 1950s, when they estimated the age of the universe, they would say about 3 billion years. If you estimated the age of Earth, it's much older than that. If you estimate the age of the solar system, much older than that. So how could the universe be younger than its stars? That was a big problem for the theory. They had to update the theory, update the age of the universe to make the Big Bang theory work. So by the time in the 1960s, that age was updated. Today we know that the universe is 13.8 billion years old, much older than its stars. Now there was this big international rivalry. The Pope at the time endorsed the Big Bang theory. The Astronomer Royal of England, the most important astronomer, endorsed the steady state theory. How would the battle be resolved? The answer arrived thanks to a discarded radio receiver that was used for communication satellites in the early 1960s. So here's this radio receiver, and this was and is still in New Jersey. 2 scientists, Arno Penzias and Robert Wilson, decided to convert that horn antenna to astronomical use. Why? Because they wanted to look for possible radio signals from the Milky Way galaxy's halo. And they were looking for those signals. A lot of scientists said, no, there's no such signals, but they pointed the antenna at the outer part of the Milky Way to look for these signals. But instead, they found a persistent background hiss, a constant noise, kind of like static you would hear from a radio. If you have an old-fashioned radio and let's say a car radio, and it's tuned not to a station, but to no station, you might hear this hissing sound. Well, that hissing sound was persistent for them, and they didn't know what it was. And they tried to rule out possibilities. One, they thought maybe it was noise from New York City. At one point, they thought it was the white dielectric material dropped from pigeons. That pigeons, in their daily business, create this white dielectric material that drops from them and dropped onto the antenna. I'm not going to say what material is, but you can use your imagination. So they cleaned up their antenna and they trapped the pigeons in this cage, which is now in the Smithsonian Institution Museum, and still they heard the hiss. Finally, they found out about a physicist who was an expert in that area, Robert Dicke of Princeton. Dicke, remarkably, had been working on his own radio receiver to try to detect the hiss from the early universe. Hadn't finished it yet. And when he found out about this hiss, he announced to his team, his group, including this guy, Jim Peebles, we've been scooped, boys, meaning that somebody beat them to the punch. Somebody beat them to the discovery. And Dicke and Peebles, who analyzed it, recognized it as cooled down leftover radiation from the early universe. And that's now 3 degrees above absolute zero. Now, this picture was from much later. This is a picture called the baby picture of the universe. And much later, satellites mapped out the hiss and saw that some parts are a little bit hotter, some parts are a little bit colder, pointing to structure in the early universe. And all of this was considered strong proof of the Big Bang theory, the fact that the universe was once very hot and that its radiation has cooled down over time. And we still experience the radiation today throughout the universe, everywhere you go. And I have to remark that I recently saw a new TV series called WandaVision, if you ever see it, and they talk about some town which is surrounded by an energy field, and they say they detect extra cosmic background radiation in that town, which I thought, that's rather preposterous. How can the universe from the Big Bang send signals to a single town? But that was part of the plot of the series. So these ideas from the Big Bang cosmology sometimes creep into popular culture, and that's how we hear about them, even if the science isn't always correct. So in 1965, the news of the day was the Big Bang was proven, and the antenna was on the front page of the New York Times, and Robert Wilson was excited because his dad just walked to a corner store, picked up the newspaper. Of course, it was a print newspaper, not an online newspaper. And the front page was this instrument that his son was using. And they knew at that time they were world famous. And they eventually won the Nobel Prize for their research. And I was lucky enough to talk to both of those scientists, interview them for my book. Now, back to Gamow. Gamow, and especially Alpher, said, well, wait a minute. We were the ones who came up with the Big Bang idea. And Alpher, in particular, calculated that there would be a radiation background in the universe. He estimated 5 degrees above absolute zero. So Gamow and Alpher survived Gamow by many years, kept publishing articles saying, look, make sure you give credit to us for the original predictions about the Big Bang background radiation. And Gamow, one of his last scientific events, went to a scientific meeting and people were asking about this discovery. And he said, well, if you lose a penny, meaning he put down this idea many years ago and someone else finds it, it's the same penny. So he told the people that, and that expression stuck in the minds of the scientists attending the conference. And, you know, the idea was Gamow really wanted credit for his work, and Alpha really wanted credit later on, which deservedly, and Alpha later would win prizes and awards for his discoveries. Back to Hoyle. Hoyle briefly entertained the idea of the Big Bang Theory, and then he started to ponder alternatives once more and thought, well, maybe I can resurrect the steady state theory. Along with two of his colleagues, he developed this idea of a quasi-steady state universe where instead of big bangs producing the helium in the universe, little bangs would create the helium. And he had this idea of these particles in space that would mimic the cosmic background radiation. And that became the quasi-steady state theory. And he held on to that idea until the end of his life. And he wrote a book where they put this picture and they said, this is our view of the conformist approach to the standard Big Bang, that all these scientists are like geese following the lead goose and not thinking for themselves. So that was his final judgment of Big Bang theories. They need to think for themselves. They need to think differently. Gamow died in 1968, Hoyle much later in 2001. Each was a maverick until the end, and they were honored, Gamow with a plaque in Washington, D.C., and other honors. Hoyle was honored with a statue in Cambridge, England. So for more about the fascinating history, there's a lot more in my book, Flashes of Creation. And now I'm going to stop here and see if there's any questions from the audience.
All right, thank you, Paul. Does anybody have any questions? I do have some questions, but if somebody wants to scoop me, that's okay. Okay, so I will start, I guess. One of the questions I had was, you talked a lot in your book about these aspects of scientists' personalities that fed into their research and made certain scientists better suited for some projects or others. Could you just comment on to what extent you think that the personalities of various scientists shape their conclusions as opposed to simply shaping what projects they're drawn to pursue? Like, did you think in your research that there's any lasting imprint of the scientists on their theories in terms of their personalities, or did you more see this as a just a more natural social factor?
Well, people try to read into the lives of Gamow and Hoyle. Why did Hoyle support an eternal universe? Why did Gamow support a finite universe? And that might be a little misleading because neither of them was a very religious person. Neither of them really dabbled in philosophy. They were both real hard-headed scientific thinkers. Now, how their personalities did shape their science was more in the way they did the science, not the conclusions they reached so much, but more how they performed their science. They were both maverick thinkers and impulsive, and they're impulsive in different ways. I was told that Gamow would call up, when he worked at George Washington University, call up his colleague, Edward Teller, every morning with a new idea. And he'd say, what do you think of this, Teller? And Teller would say, it's a great idea, or that idea is not going to work, it's bonkers. And then Gamow would either pursue the idea or move on to another idea. So Gamow kept moving on. He kept switching fields. He dabbled in biology. He made some contributions to genetics. He kept kind of moving around. And one fault that he had is if calculations took more than a few days, and especially more than a few months, he got kind of bored, and he would try to delegate everything to other people. And sometimes he made mistakes that way. He'd do a quick calculation, think it was right, send it off for publication, and it would turn out to be wrong, and then it would have to be corrected. So if he was on target, he could stay up all night, do a quick calculation, and revolutionize science, as he did with nuclear fusion. If he was off target, he would stay up all night, do a quick calculation, and then that might turn out to be like, a false path. And he would acknowledge that and just move on to something else. He kind of just wanted to have fun. Now, Hoyle's impulsivity got to him in a different way. He would come up with an idea, but then he was very, very persistent and stubborn about it. And he would stick with the idea and he would change it, but he would be very resistant to change the idea. One example was steady state theory. He also, in his later years, came up with this hypothesis that the universe was seeded by extraterrestrial life forms, but he never quite proved the idea, but he kept arguing and arguing and arguing it. It's called the panspermia model. And even though a lot of scientists said he was getting very, very far-fetched with the idea, especially when he started to say that all diseases came from space. And people said, well, wait a minute, where's your evidence for that? He was very stubborn and clinging to his ideas. So that served him well in the beginning when he was persistent about good ideas, but didn't really serve him well in the end of his life.
Colin in the chat has a question. He says, did any of the book relate to telescopes around the globe, such as Chile and their research, or mostly Hubble and the background radiation?
So my book is a historical book. It's set in the 20th century. So it takes place mainly in the 20th century. So the telescopes that you're familiar with are not really mentioned so much in this book. I mean, there's a little bit at the end bringing the book up to date, but it's more like a thriller looking at science in the past. If you want to really feel how science was done in the 1940s, 1950s, 1960s, and experience that rather than a look at modern innovations from the 21st century. I dealt with that in another of my books, which is now somewhat dated since that book is some years old, but Edge of the Universe, which is a few books ago, I tried to look at contemporary cosmology, and I think that book came out in 2012. So it's somewhat dated now. It's about 9 years dated. But this is a history book, history of science book, not a modern book. So I don't talk about telescopes in Chile. I talk more about telescopes in California, such as Mount Wilson Observatory telescope, where Hubble made his discoveries 100 years ago.
I had another question for you about it's sort of religion and science question. One of the episodes you mentioned in your talk was where Pope Pius XII blessed the Big Bang cosmology before it became scientific orthodoxy. It was interesting to me in the book how you drew a contrast between Gamow, who as an atheist was pretty eager to accept this kind of papal cachet, but George Lemaitre was a priest who had been really behind the Big Bang, but he seemed a bit more squeamish. Did you see that distinction between the two of them as just a personality difference, where Gamow was a bit more of a self-promoter, or did you see it as a difference in their view of science and religion?
Yeah, well, Gamow didn't really like ideology. He didn't like orthodoxy. But at the same time, as you said, he was a self-promoter. He was a bit of a ham. He really loved praise and loved it when like key figures like the president of George Washington University, he looked to for praise. And he liked the idea that people would pick up his book and say, wow, this is remarkable. So he sent a copy of his book to the Pope. He sent copies of his papers to the Pope and just kind of wanted to like get them to say like, wow, this is really cool stuff. That's what he was looking for. And Lemaitre, on the other hand, was a priest. He was very humble, very, very quiet man. So he never promoted the Big Bang Theory, even though he was arguably much more pivotal in the early stage of the Big Bang Theory than Gamow was. So Lemaitre's Primeval Atom, he wrote a book about it, but he would never like go on the radio and say, yeah, this is, you know, absolutely the description of the universe. Like he was very quiet about promoting his idea. And in fact, before Hubble made his discovery, Lemaitre, as I mentioned in my book, made predictions about the expanding universe. And then it was in a paper that was in French and published in Belgium. And then when he translated the paper into English upon Hubble's discovery, he didn't translate the part where he made the predictions just because he thought Hubble's predictions were superior. Hubble's calculations are superior. And he was humble enough not to say, hey, I was the first one to do it. He just wanted like scientific accuracy, which I thought was really cool that he had this humility, modesty, and just wanted to get the word out about science.
Joshua, do you want to ask your question over verbally or over the chat?
Yeah, I would love to ask verbally if that's okay.
Okay, you're on.
Can you hear me all right? Fantastic. So I'm not a physicist. I'm an organic chemist, so I'm not, I don't know what I'm talking about, but I do like to watch astrophysics videos on YouTube. So my question is, I've seen a lot of modern videos that are sort of questioning the idea that perhaps the Big Bang is not as settled science as we thought it was. But my question is, one, do you think that this is settled science? And two, if it's not settled science, if the personalities of these scientists had been less self-promoting, do you think that we would be farther along in exploring other possibilities than we are currently?
So to answer your question, first of all, when you take the Big Bang Theory, it's become really kind of an industry. It's much more than the theories of Lemaitre or Gamow. There are many different predictions, and there are also variations. For example, the standard model involves a period called inflation, where the universe in the very beginning expands very, very quickly, ultra rapidly, and that's how the matter and energy is created. So when people say the Big Bang is not settled, what is settled is everybody pretty much believes that the observable universe, meaning what we can see around us, was once much more compact and much hotter. So if you call the Big Bang Theory the idea that the observable universe, everything we see in space, was once much closer together and much hotter, practically any scientist believes that. But what's different is this idea of what happened in the early stages of the Big Bang, whether there was this period of inflation, whether there could have been something preceding the Big Bang. So there's some theories about that. And what is the destiny of the universe? What is the dynamics of the universe? So there are many, many variations. So to say the Big Bang is not settled, it's that we don't really know the entire evolution of the universe or what preceded, if anything, the hot early stages of the universe. But we do know that the universe was once a hot, to use a dated term, a fireball or a really hot compact object that in which energy was very closely distributed, of a very high density. So that's what the state is now. In terms of the self-promotion of Gamow and Hoyle, it really didn't affect the history of cosmology, because by the time in the 1960s, a younger generation took over, including people like James Peebles, who I mentioned, who played a major role in the development of physical cosmology. And if you want to hear more about that, we've invited me and others to the APS April meeting in New York. James Peebles himself is going to be talking about a century of physical cosmology. He won the Nobel Prize relatively recently for his contributions. And there are many, many other physicists who pushed the story forward. By the time of 1965, Gamow's role was very minimal. Hoyle's role was very minimal. A younger generation took over.
I have a question from Ikra. I'll ask, I think, what the spirit of the question is. This is outside the scope of your book, but she asks, what did Stephen Hawking have to do with the Big Bang Theory ultimately?
Well, actually, I do mention in my book.
Oh, okay, sorry.
So in the last chapter, or the second to last chapter, so Stephen Hawking took Einstein's general theory of relativity, and he, based on the work of Roger Penrose, another physicist, on black holes, Hawking imagined that the universe was kind of like a black hole in reverse, a time reverse black hole. So Penrose proved that if you have a glob of matter and it's massive enough, no matter what the shape of the matter is, you compress it and it becomes this object of infinite density called a singularity, which has, the density is literally infinity. It's all this matter compressed into a single mathematical point. And Hawking showed around the same time in 1965 that if you run the universe's history backward in time, no matter what the universe looks like today, run that as a movie backward in time, you reach a point where everything is infinitely dense, and that's a singularity. And that shocked everyone in 1965, because along with the experimental evidence for the Big Bang that showed that the universe literally emerged from a point of infinite density, and even some of the Big Bang people like Gamow and Robert Dicke and so forth didn't really believe that. Lemaitre didn't believe that. They thought it was a finite clump of matter, but Hawking showed it was a point of infinite density. So that was Hawking's monumental contribution to cosmology.
Okay. I have at least one more question. I'll leave it open if anyone else wants to ask. I think it was a special thing to read this book because it's about two scientists who, like you, were also actively engaged in science outreach in addition to their more technical science research. Could you just comment a little bit on the ways that the sorts of thinking that go into science outreach and science writing are the same as the types of thinking that you would use for scientific research, and also maybe a little bit how they might be somewhat orthogonal to the ways of thinking you use for science research?
That's a very good question. And I have to say, historically, there are very few scientists who are excellent scientists and also excellent popularizers. So there's maybe a handful. Carl Sagan, who some of you may have heard of, the guy who did the original Cosmos series before Neil deGrasse Tyson. He was a wonderful writer, a wonderful popularizer. He had his own TV series. He did contribute some key scientific papers, but no one would say that he was an important astronomer of the 20th century, one of the most important astronomers. They wouldn't rank him highly. He wasn't doing material that was anywhere near Nobel Prize winning material. Whereas Gamow and Hoyle were both nominated for Nobel Prizes, and Hoyle arguably should have gotten a Nobel Prize for his stellar nucleosynthesis theory. There was some politics involved. And yet Hoyle is considered ranked up there with some of the greatest science fiction writers. So, and Gamow is ranked up there with some of the greatest science popularizers. So this is a unique case. That's what made writing the book so enticing for me, is to have this unique combination of excellent science and excellent popularization. It seemed really incredible that they could do that. Now, in my own case, I got my PhD from Stony Brook University, and it was very mathematical. It was calculations in general relativity. And then, you know, I worked on it for a few years, and then I just really, I wouldn't say I burned out, but I just felt a little bit like a living zombie, just doing these calculations all the time and not really getting out and meeting with people and talking about other ideas. And when I was an undergraduate, I really liked the idea of being an undergraduate. And I'm sure it's the same in Centenary, that that you can like take courses in all these different areas and study all these different things. But in graduate school, suddenly I had to focus and just study these equations and work on the calculations and work on computations. And toward the end of my time at Stony Brook, I was going a little bit, I was getting a little bit upset about being so closed off. And I started going to this poetry slam on campus, and mainly undergraduates. But I started writing what, in hindsight, and I think I knew at the time, wasn't particularly good poetry, but it just felt liberating to like be doing something different from calculations. And then when I got my first job, I was asked to give a talk about the nature of time. And once I was putting together for the materials for the talk, I just really felt a lot more like working on a book and doing something creative than just doing more calculations. And since then, I've gone back and forth. I've done technical papers, I've written books, and I've written research articles, scholarly articles in history of physics. And I like doing all those things, but for me, you know, kind of touching base with culture and creative stuff is in some ways more rewarding than doing the calculations and in cranking out like numerical results. As much I've kept up with that, I still have a paper in submission which involves calculation. So I continue to do that, but I find it more rewarding to do the writing. And I think that they involve very, very different skills. And in my case, I feel much more comfortable with doing history of science and the science writing. And with the calculations, I kind of feel like, well, I can do them, I can get published, but I'm not going to make a breakthrough with my scientific calculations, unless I get incredibly lucky at some point. But they're not really major things. They're more things like, well, take a variation of some calculation and get it published. Maybe someone else's work, and try some other avenues and do a calculation, check the calculation, and get it published. So to me, those are on very different levels and very different skills. So I don't really see too much in common with science popularization and science, except for the fact that you really have to have a solid basis in science and understand science to popularize it properly.
Okay, are there any other questions? Okay, let's thank Dr. Halpern again.
Thank you.